We'll look at some properties of functions in section 2.1, beginning with what it means for a function to be increasing on an interval, for what it means for a function to be decreasing on an interval, and what it means for a function to be constant on an interval. This is particularly helpful for a function whose domain happens to involve the passage of time. A lot of times the independent variable will be t for time, and if, for example, you've got a situation where you want to express the value of an investment portfolio as a function of time, you would like for that to be increasing rather than decreasing as time passes. But stock market and various investments fluctuate in value, so it could be that it increases over some time intervals, decreases over other time intervals, and then increases some more. So when we define this, it'll be over an interval rather than for the entire function. MAC. Oops, in the wrong folder here. Let's get this in fall 2017. MAC1105. Something else on the clipboard. So for a function to be increasing, we have a precise definition, and then we have a way to figure it out by looking at the graph, if we have access to the graph of the function. F is increasing on an interval I if its graph rises as we go from left to right across that interval. Now, the only types of intervals that we'll consider in this class when you're doing your MyMathLab homework, it's going to want open intervals. That is, we'll simply exclude the endpoints of the intervals from consideration. If it's a question about the domain of a function, we may have to include the endpoints or we may not, depending on the situation. But if it's a question of, is it increasing on the interval, is it decreasing on the interval, even if we've got a function that's increasing for a while and stops increasing and starts decreasing, that point where it stopped, we won't include that in either the interval where it's increasing up to that point or decreasing down from that point. So the official definition, I do have to mention this, if we've got, say if we're considering an interval, an open interval, for any x sub 1 in the interval and x sub 2 in the interval, we say it's increasing if when we evaluate the function at x sub 1, and we'd get this number, f of x sub 1, and we evaluate the function at x sub 2, and we get this number, f of x sub 2, if x sub 1 is less than x sub 2, then the function values have that same relationship. As we go from left to right, we go from down to up. The function values get greater and greater. But it's easiest to see if we have access to the graph, if the graph is rising along that interval. Now, I want to keep in mind that when we say a function is increasing on an interval, it's a subset of the x-axis. We don't want to say a function increases from a point to a point. That's not what's going on here as far as how we describe it. If the graph is rising between, let's say, x equals -2 and x equals 4, we would say from this picture, and I suppose I should maybe change my endpoints just a little bit, say this, we would say this function f is increasing on the open interval from -2 to 4. We're talking about a portion of the x-axis where this increasing or decreasing is happening. It looks like the point that has an x-coordinate of -2 and a y-coordinate of 4, but we're not talking about that. We're talking about the portion of the x-axis where the graph is rising. And so that's how we'll describe the interval where this function is increasing. Let's look at the decreasing picture. F is decreasing on an interval I if its graph is falling throughout that interval. That is, if for every x sub 1 and x sub 2 in that interval, where x sub 1 is less than x sub 2, when we evaluate the function, f of x sub 1 is going to have what relationship to f of x sub 2? Spoiler alert. It's going to be greater. It's the reverse relationship. X sub 1 is less than x sub 2. X sub 1 is on the left, x sub 2 is on the right, but when we evaluate the function, the relationship reverses. F of x sub 1 is actually way up here, and f of x sub 2 is way down here. So it's greater than. Now, if I look at the same interval, and I'm going to assume the graph keeps on going to the left, but since it's not in the picture, maybe I shouldn't do that. Let's just consider the interval from 0 to 4. I'm going to say f is decreasing on the interval whose left-hand endpoint is 0 and whose right-hand endpoint is 4. That interval right there. That's where it's decreasing. To the left of that, maybe it's increasing. Maybe if we look far enough to the left, the graph is going up, up, up. We can't see it. We don't know. But it's certainly decreasing on the interval from 0 to 4. And then thirdly, this is not going to be as common a situation if the graph goes straight across. Doesn't go up, doesn't decrease either. F is constant on an interval I if its graph is horizontal on the interval. Basically a horizontal line segment. It's going straight across. So pick any x sub 1, pick any x sub 2 in the interval, and evaluate the function at each one. That is f of x sub 1, and it's going to equal f of x sub 2. Same function value. It's not a very exciting graph if it's going straight across. But we say the function is constant on the interval. And again, it looks like this goes all the way from -2 to +4. So for this one, I'm going to say f is constant on the interval from -2 to +4. We want to say, where is it happening? It's this portion of the domain. This portion of the x-axis is where this is happening. I've got some examples. Does this seem simple enough? It's rising, it's falling, it's going straight across. It's increasing, it's decreasing, it's constant. Because the examples are going to ask us where. Where? What's the interval where it's happening? So we've got a graph. And hopefully we'll be able to tell where it's increasing and where it is decreasing. So example 1, find the domain and the range of the function. I need to be clear in any graph that I give you on the test where the graph actually starts and where it stops. I think the arrow makes it clear that the graph extends infinitely far in the direction that it's pointing. So it would continue. If we wanted to continue it, it just keeps on going up, up, up in the direction that arrow is pointing. The other one is maybe not so clear. Really, if the graph, if the intention is that the graph extends infinitely far up that way, upward to the left, there should be an arrow there, and there's not. If the intention is to communicate that it stops right there, or maybe starts right there, if you want to think of it like that, there should be a little dot. Either a solid dot if we want to include that point, or an open circle if we don't. So I'm going to put one, and just let you know that if this had been a test, it's maybe not completely clear what's going on there. So I'm going to put a dot there. I'm going to label that point. Its x-coordinate is -7. Its y-coordinate looks like -4. So the graph does not extend beyond that point in that direction. It doesn't go to the left. It doesn't go up from there. That's where if you want to think of it as starting right there. That's fine. So We want to find the domain and range. We didn't do this a whole lot by analyzing graphs when we looked at functions in Chapter 1, but when we've got a graph of a function, the domain is everywhere that it's the portion of the x-axis that the graph occupies. So we look at the x-axis and we say, where are there points that have those numbers as their x-coordinates? So we begin by asking ourselves the question, how far to the left does this graph go? How far to the left? Looks like -7. Goes as far to the left as x equals -7. If I were shading the domain on the x-axis, I could start it right there at -7 with a bracket, because it includes -7. How far to the right does this graph go? It just keeps on going. If we're wondering, is 10 in the domain? Well, it looks like it is. It looks like there's a point on the graph up here somewhere that has an x-coordinate of 10. If we're wondering if 15 is in the domain, well, it looks like it is, because it looks like if we go way up here somewhere, there's going to be a point on the graph with an x-coordinate of 15. Since the graph just keeps going up, 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 and to the right, 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 it'll go as far to the right as we want it to go. So the domain of this function is going to be from -7 to +infinity. Okay, pick any number in that interval, there'll be some point on the graph that has that number as its x-coordinate. In fact, exactly 1 point on the graph with that number as its x-coordinate. For the range, we're considering the portion of the y-axis that the graph occupies. So we ask ourselves questions like, how low does the graph go, or how high does it go? First of all, how low does this graph go? -9. -9 is the y-coordinate of the lowest point on the graph. If we want to label that point, there it is. That's, looks like -6 maybe, -9. So if I'm shading the y-axis, the portion of the y-axis where the range is, I would begin something like that. And let me say this, when we're reading a graph, I think it's natural, because a lot of students will do this. It's natural to read a graph from left to right, and then I think it may also be natural to read a graph from top to bottom, but when trying to determine the range of a function, you want to read it in the order that the y values are increasing. So that would be from the bottom to the top, from -infinity to +infinity. So we start toward the bottom of the graph there at -9, and then we ask ourselves, how high does the graph go? How high does it go? Infinity. Now, another question I should have asked this with the domain, and so I'll ask it now with the range. Are there any gaps in the graph where it's broken, where there's a discontinuity, where maybe some number in between -9 and +infinity might be omitted? I don't think so. I think the graph, we could, if we start at the point -7,4, we could just kind of draw a line segment, and then up another line segment, and then over, and then up, and we really don't have to pick up the writing utensil in order to sketch this graph. So all the numbers from -7 to the right are going to be included in the domain, and all the numbers from -9 up are going to be included in the range. So for the range, we can go with the left-hand endpoint, -9, all the way to +infinity. Now, I want to know the intervals where it's increasing, intervals where it's decreasing, intervals where it is constant. So I'm going to begin by saying f is decreasing on, there's one interval, I believe, where the function f is decreasing, and I'm not going to include the endpoints. Just going to include, well, I'm going to write the endpoints. We're going to make it an open interval, because that's the way my math lab's going to expect it. We're not going to have to ask ourselves, shall we include the endpoints or not? We'll just exclude them. If we're thinking about point to point, I'm thinking, you're thinking, the graph falls from there to there. But what's the set of x values where that's happening? The x values where that's happening are these. Doesn't take long to get from where it is at -7 all the way down to where it is at -6. So it decreases as long as x is between -7 and -6. And once x gets to -6, it stops decreasing and begins to do what? The graph begins to rise, the function begins to increase at that point, as soon as it gets to -6. So f is decreasing on the interval from -7 and -6. F is increasing if we look at where this is happening. The graph is rising along that line segment. What's the portion of the x-axis where that's happening? Here we go. -6, when x gets to -6, it starts increasing. When x gets to -2, it stops increasing. So -6 to -2. So it gets beyond -2. It's not increasing anymore. So we could say f is what? Constant on, all right, what portion of the x-axis, where is this happening? From -2, where it stopped increasing, all the way over to the print is small. My apologies to those in the back row. All the way to 5. -2, it looks like all the way to 5, it's constant. It has that same value. It's constantly equal to -2 all the way over there. And then when it gets to 5, once again, oops, is increasing. Oh, and I guess I'll go back to blue. This is the, and I'm just not happy with the way I originally extended that graph. If I can draw a little bit straighter line there. There we go. So it begins to increase at 5, and over what portion of the x-axis does that continue to happen? Infinity. It keeps on going. So 5 to positive infinity. It's increasing on the interval from 5 to positive infinity. So keep in mind, it's always an interval that you want to write. It's always a portion of the x-axis. Those intervals along the x-axis are the ones we're trying to describe there when we're asking, is it increasing or is it decreasing? And when MyMathLab asks this, it's going to want you to put parentheses rather than the square brackets. Okay. Did you bring your calculator today? Yeah. We'll need them in just a little bit. This first graph, I think we'll be able to look at it and then identify where these key points are. But the next one, we'll use the calculator to find the key points of a particular function that we really can't find them otherwise. Make the print a little larger. Relative maximum and relative minimum points is a somewhat sophisticated looking definition there. Let me draw the picture and then try to indicate what the definition we're looking for. If we've got a function, and I think I can cover both of these on the same picture. Say the graph does something like this, and it reaches the point, I like to characterize this as the top of the hill. Okay, it might not be the highest point on the graph. It might be the graph goes higher and higher, maybe infinitely high, but there's this point at the top of a hill, and we call this a relative maximum point. I'm going to say that's A, F of A, relative maximum point. These particular points are interesting in applications if it's a situation where there's a quantity that we want to make as great as possible. If we can affect the profit that a company makes by determining various the values of various variables, including, say, the price point. If we look at the price point and can do some mathematical modeling to determine if we can express the total sales, the total revenue, ultimately the total cost and total profit in terms of our price point, we want to make the total profit as great as possible. So if it could help us determine what price tag to put on an item to make the profit as great as possible, it would be a useful thing to do. So we like to find points on the graph where it looks like it's as high as possible. If we're trying to control costs, we might want to make that as low as possible. We might want to minimize the cost. So the point, and I'm going to label it a little bit differently. I'll call this B, F of B for this relative minimum point. This relative minimum point, I like to think of that as a point at the bottom of a valley. And if we could find the location of a point such as that, it might be that the x-coordinate will help us determine how to keep a quantity just as low as possible if we want its value to be as low as possible. We want to see if we can analyze a graph and determine the location of these points using the graph, and we may also have to use a calculator if we're given a function to generate the graph and find the location of these points. There's one other feature that these points tend to have. These points tend to occur at places where a function stops increasing and starts decreasing, or stops decreasing and starts increasing. So if we know the locations of these points, we can answer questions like in the previous example, find the interval where the function's increasing, find the interval where the function's decreasing, and there's not many of these where the function will actually be constant on an interval, but certainly the intervals of increase and decrease. Example 2. The term maxima and minima, basically plural of maximum and minimum, collectively they're referred to as extrema. If you don't want to say find the relative maxima and relative minima, you could say find the relative extrema, and that covers both. So find the relative maxima and the relative minima of the function graphed below. Are the maxima and minima turning points? And here's the thing. I believe anytime my math lab asks you, are these turning points or not, the thing to do is just say yes. It's kind of an unusual situation for a relative maximum not to be a turning point. There's a special case where if you've got a function that's constant on an interval, by the way we define relative maximum and relative minimum, a point on there is technically both a relative maximum and a relative minimum. It's a relative maximum because there's no point close by that's greater or that's higher, and it's a relative minimum because there's no point close by that's lower, where the y-coordinate is less. It's kind of a strange case. So we typically don't consider those. Those would be examples of relative extrema that are not turning points. It doesn't stop increasing and start decreasing or vice versa. But if there's a case like this one where it's at the top of a hill, or this one where it's, I don't know, I want to call it a valley, it's just sharp turn there, or this one, at that mountain peak perhaps, the graph actually does turn. Stops increasing, starts decreasing. So all three of those would qualify as turning points, where the turning happens. So let's indicate the coordinates. It's close. I mean, if you want to call it negative 2.9 something, that's fine. I'm going to go ahead and call that negative 3, 4 for this relative maximum point. And this one seems clearly 1, 0 for this relative minimum point. And this, we're going to have to call that 2 point something. Might have a preference. 2 point, what's the x coordinate? 5? 2.5? 2.5, and I think we can go with 5 for the y coordinate. So we have two relative maximum points, one relative minimum point. It says assume integer coordinates, but there's no way I can do that. The first two were close to integers, but that third one, I need to work on my graph there. I'm going to move on to the next example. It may be a little bit of a challenge to get the picture in our calculator to look like this picture. Now it does give us kind of a hint as far as what the y max should be and what the y min should be. It's not going to look just like this if we graph this in the standard viewing window. But let's see if we can do as much with this polynomial as we know how to do so far. Previously, we've found zeros of polynomials like this. We had a problem like that on the test where we needed to find zeros of a third degree polynomial. Let's find all the relative extrema, relative minimum points, relative maximum points. And then once we've done that, we'll be able to determine where f is decreasing and where f is increasing. Oops, there we go. And let's see if we can get our calculator to look just like this. Clear it. Y equals. If you're working with a newer operating system, of course, you know after you type the exponent, it doesn't quite look like this. Press the right arrow so the graph moves off the exponent so you can type the plus, and the plus doesn't end up in the exponent. I'm going to look at my viewing window and see what it is. This is the standard viewing window. If I simply press graph, it'll show me a graph, but it won't show me the complete graph. Make sure that we're all in the same spot. I'm going to press zoom followed by 6. And this will give me the standard viewing window with an x min of negative 10, an x max of positive 10, y min of negative 10, y max of positive 10. And for high degree polynomials like this is usually a picture. The graph kind of zips up and down through the standard viewing window if it has any points in the standard viewing window at all. And if we're trying to get a handle on where it's increasing, where it's decreasing, where these relative minimum and relative maximum points are, we need to slow the graph down. Slow it down. And we can accomplish that. I press the window button. Press the window button. We can accomplish this by going with a lower y min instead of negative 10. I would start with negative 100. Just multiply that by 10 and see if that helps. So be sure and use the negative sign there rather than the minus. If you use the minus, then it may give you a syntax error. But if you go with the negative sign, negative 100 to positive 100, and then a y scale of 10, so we don't have so many tick marks jamming up the y-axis. it'll slow it down, and you can see the graph a little bit better. I think I'm going to have to make one more change here, but this will be a definite improvement. This is almost enough. By slowing the graph down this much, we're able to see now this relative minimum point, this relative maximum point, and there's another relative minimum point down here, and if I'll just set the y min a little bit lower, it's probably negative 200 or so, maybe not quite that much, but if I set it from negative 100 down to negative 200, might be able to see this. So window, leave the y max where it is, but negative 200 I think is going to be better for the y min. And the y scale is probably okay, but 30 tick marks may make it look kind of jam-packed graph. Yeah. The y scale is pretty useless at this point with that many tick marks on it. So here's our graph. We'll do the B part first. Let's find the relative extrema. I may actually skip the C part since we've kind of been there and done that. But let's look at the B part and see if we can find the relative minimum points, relative maximum points. I'm going to focus my attention on this one on the far left, down in the third quadrant. The procedure for finding them looks a lot like the procedure for finding zeros. Basically, second button, followed by the trace button that has the calc up above it. Second, calculate. And then we're looking for a point at the bottom of a valley, so it's a relative minimum point. So 3. It's going to ask for a left bound. If we give it a left bound, it's going to ask for a right bound. If we give it a right bound, it's going to ask for a guess. Just like it does when we look for zeros. So if we look at the point, it kind of looks like the x-coordinate of that point is about negative 3. In fact, it may be exactly negative 3 for this example. But it looks like it's about negative 3. So to tell the calculator exactly where to search for a left bound, I need to tell it a number that's a little bit less than negative 3. For a right bound, I need to tell it a number that's a little bit greater than negative 3. So I would think maybe negative 5 to negative 1. That would work. You could go with different numbers, but that would give it a pretty good idea. If we go too large, if we go negative 10 to 10, then it's not going to find this relative minimum. It's going to find that one down there, because that one's lower. But if we keep it not too far away from the negative 3, it should find what we want. So let's go negative 5 for left bound, negative 1 for right bound, and then for the guess, I usually just press enter and just use whatever my right bound was as the guess, and it seems always to work. At some point when that stops working for me, maybe I'll stop doing it. So I'm going to use negative 1 for my guess. And it finds, I'm going to say that's close enough to negative 3 to call it negative 3, negative 2.999999. In fact, it is negative 3 in this example. If you take negative 3 and physically substitute that for x there, and there, and there, and there, it will give you exactly negative 27, and that will be the relative minimum point. I'm going to capture this graph. Enlarge it a little bit. So negative 3, negative 27. So there are a couple different ways we could say this. We could say negative 3, negative 27 is a relative minimum point. Another way we could say this, if we want to talk specifically about the x-coordinate and the y-coordinate, we could say this. We could say f has a relative minimum value of negative 27. Whenever we're talking about function values, it's always the y-coordinate. When you evaluate a function, you get an answer. That's the y-coordinate of the point on the graph. So So it has a relative minimum value of negative 27, comma, and if we want to bring the x coordinate into it as well, and the relationship there, we can say which occurs at x equals negative 3. Basically, that tells us if we evaluate the function a little bit to the left of negative 3, say negative 3.1, we're going to get something that's more than negative 27. If we evaluate it a little to the right of negative 3, say negative 2.9, we're going to get something that's a little greater than negative 27. So negative 3, it bottoms out, and that's where that relative minimum point is. Let's find another one. Let's find that relative maximum point. Looks like it's right about there. I think the x-coordinate probably is 1 in general. It's not going to be an integer, but, sorry, negative 1 is what I should have said there. It looks like it's going to be negative 1. Second, calculate maximum. Looking for that point at the top of the hill there, left bound. Well, if I think it's happening right at negative 1, I want to choose a left bound that's a little bit less than negative 1. Maybe negative 3 would be a nice left bound. And for my right bound, I want to choose a number that's greater than negative 1. I could go with 0. I could go with positive 1. Maybe 0. Oops. Just 0. There we go. And I'm going to use 0 for my guess. So I'm just going to press enter. Using 0 for my guess, and it searches and it finds, I'm going to call this negative 1. I think that's close enough to negative 1 to call it negative 1. And in fact, if you were to evaluate this function at negative 1, you would get exactly 37. And this is the point at the top of the hill. Negative 1, 37. Negative 1, 37 is a relative maximum point. Is this a fairly easy thing to do? Find a point like this. The calculator, top to bottom of the valley, top of the hill. One more. Second, calc minimum. I believe this is the absolute lowest point on the graph. Looking for the point that right down here at the bottom of this valley that appears to have an x-coordinate of 2. So for left bound, I'm going to choose something a little bit less than 2. I'm going to choose 0. For the right bound, I'm going to choose something a little bit greater than 2. I'm going to choose 3. And for the guess, I'm going to choose 3 again, just because it's convenient. It's going to search and it's going to find. I think this is close enough to 2 to call the x-coordinate 2. If we evaluate the function at 2, I think we get exactly negative 152, and this is a relative minimum point. So 2 comma negative 152. Let's see, no rhyme or reason to the color scheme that I seem to be using here. Negative 152 is a relative minimum point. At this point, can you tell the intervals where the function's increasing and where it is decreasing? If we go all the way to negative infinity and we start heading from left to right, what's the first type of behavior that you would use to describe the function? What's it doing? Is it increasing? Is it decreasing? Is it constant? From negative infinity to somewhere where it turns. Say from negative infinity to negative 3. Is it increasing? Is it decreasing? Is it constant? Decreasing. Decreasing. When it gets to that relative minimum point, it stops decreasing and begins to do what? Oops, what did I do? It turns, it stops decreasing and begins increasing. And we want to indicate the portion of the x-axis where that increasing is happening, say from there to there. The graph is rising whenever x is in between those two values. What are those two values? -3 is the first one. And then what's the x-coordinate where it stops increasing? That one right there, it looks like. -1 stops increasing. And it starts doing what? Decreasing. Decreasing on the interval from where it started at -1 to where it stops decreasing. I'm just running out of colors here. Yes. Decreasing from -1 to 2. Along that interval, the graph is falling. And it does not turn again. So whatever it starts doing at 2, it keeps on doing that all the way out to positive infinity. F is blank on the interval from 2 to positive infinity. You have one of these calculator problems on the test, and you can't decide increasing, decreasing, or constant, and you have to guess. Don't guess constant. Okay, these polynomials, they increase on intervals, they decrease on intervals. Unless it's a constant polynomial, f of x equals 5, that goes straight across, it's not going to be constant on any one interval. Now, if it's a graph that Mr. Mizell has just contrived, where was it? Was it there? Was it there? There it was. That might be constant on an interval. You see that going straight across. That's going to be constant. But if it's one that the calculator generates for you, it might be increasing on interval, decreasing on interval. It's not likely that that's going to be constant on a given interval. Example 4. Historically, this example shows up in the context of quadratic functions. F of x equals some expression with an x squared term in it. And we have a special technique for finding the middle point, the highest point or the lowest point on the graph of a parabola. Well, we haven't talked about quadratic functions yet. We will eventually, but haven't yet. This textbook is kind of taking a different approach to a problem like this, just saying, here's a situation where we need to build a function. It's going to happen to be a quadratic function, but that's not going to be real important. We're not going to have some formula for telling us the coordinates of this highest point or the coordinates of this lowest point. We're going to use our calculator to help us find that point. And it's going to give us kind of a general procedure for solving a problem like this without having to memorize a formula. And maybe that's a good thing. I hope the quadratic functions in that section when we get there don't feel shortchanged that we've already done a problem like this. But a little bit different approach than I'm accustomed to, and I hope it works out really well. A rectangular pen enclosure. I'm going to fence it. Going to have one interior partitioning wall, maybe right down the middle. Doesn't have to be exactly right down the middle, but just so that the wall that does the partition in the middle is parallel to one pair of exterior sides. We're going to form this, and I guess it'd be pretty good size. We're going to use 900 feet of fencing material. So we're going to use the same type of fencing material around the outside. We're going to have to enclose this, going to have to enclose this, enclose this, enclose this, and we're going to use that same type of fencing material right there as well. So if we add it all up, we'd kind of take a tape measure or whatever, and we add it up, this many feet plus this many feet plus this many feet plus this many feet plus this many feet as well. Add all that up. We want to use 900 feet of fencing material. So the entire perimeter plus that interior partitioning wall, 900 feet of fencing material. But we want the total area enclosed by the fence to be as great as possible. I mean, we can make it where it's really, really long, maybe almost 450 feet long. Not quite though. If we made it 450 feet long on one side and 450 feet long on the other side, what would be the problem with that? That's all of our fencing material, and then we can't put the other sides on there. So we could make it a little shorter than 450 feet, and then enclose it. I don't know what we're gonna put in there. Livestock would have to be really, really skinny in order to go to and fro, and it's not going to be a whole lot of area if we do that. We could make it the shape of a square, or maybe a rectangle that's not quite square. But different shapes that we put on this are going to result in different areas, and maybe some examples would help to see that. We want to express the total area enclosed by the fence as a function of x, which is the width of the pin. So let's call this the width. So that's x, and that's x, and that's x. Express the total area as a function of x, and then find the maximum area that can be enclosed by the fence and the dimensions of the fence that produce this maximum area. All right. Well, what if somebody told us, all right, we're going to make this thing 100 feet wide. 100 feet. Is that enough information to calculate the area? We want it to be a function of the width. So if someone tells us the width, it's input. Oh, I'm so sorry about that. That's me. Not even going to look at it. I'll be able to withstand the suspense there. Input 100 feet for the width. The output needs to be the area. Can we calculate the area here? This has got to be 100 feet, and that's got to be 100 feet. Ooh, not 1,000, just 100. How are we going to tell how long this is? How many? We've used 300 feet so far. How much do we have left? 600 feet. So I'm thinking half of it there, half of it there. So 300 feet. And then 300 feet like that. That uses all 900 feet. What's the area if that's the way we choose to build this? Area equals length times width, since we're dealing with a rectangle. So 300 feet times 100 feet. And we multiply feet by feet, we get square feet. What if we multiply 300 by 100? 30,000 square feet. So if we want to build it like this, if we input 100 feet, the output is a unique value, 30,000 square feet. So it seems reasonable that we can express the area as a function of the width. Let's try a different width and just see how that compares. What if we go not 100, but maybe, how wide do you want to make this thing? 225? Can we do 225? I suppose so. I don't know if you'd call it the width, but I guess we could do that. And I'm afraid, I don't know. Let me do it more like this. There wouldn't be anything wrong with doing it like that. 225. like that. So how much fence? 225 and another 225 and another 225. Is that like 675? Yeah. How much do we have left? $225, but we've got to cut that in half. What's half of 225? 112.5. So 225, and that's 225. I'll check and make sure it adds up to 900. I want to use all 900 feet of the fencing material. What is the area of this one? I'm going to call 112.5 the width. And 225 the, I'm going to call that the length. I call it 225 the width. Is it maybe not quite 30,000, or is it? 25,312.5 square feet. Different dimensions, different area. Certainly the 100 by 300 encloses more area than the 225 by 112.5. But in either case, if we input the width, there's a unique area that's determined. So I think it makes sense if we just call this X, we should be able to express this other dimension in terms of X. So that's X, and that's X, and that's X. How much have we used so far? X plus X plus X. How much is that? 3X. 3X. So we used 3X. Now we want to use a total of 900. So how much do we have left? That what we've done in each case, we had 100, 100, 100, and we subtracted that from 900, and we got 600 that we needed to use, and then we knew we need half of it up there and half of it down there, so we had to cut that 600 feet in half and put 300 feet, probably help if I had the picture there I could point to, 300 feet up top, 300 feet down at the bottom as we look at it. So if we use 3x feet, and we want to use 900, we have 900 minus 3x left. We want to cut that in half, so I believe it's 900 minus 3x over 2 up there, and 900 minus 3x over 2 down there. And I think if we take x plus x plus x plus each of those, it's going to add up to 900. You're going to get the x's to cancel, and you're going to have 900. What's the area of this? The length is 900 minus 3x over 2. The width is x. Any chance we're going to be able to punch this into a calculator? The fraction is a little troubling. Could we simplify that a little bit maybe? And it would be a little bit less fearful. I'm going to write this. Notice, you would read this a of x. I'm actually using function notation for this area function. In some context that could look like a times x, but that's a of x, the way I'm writing that, if you want to scribble that in the margin. If we write it 900 over 2 minus 3x over 2, that might help us to punch it into the calculator. We could write this as 450 minus 3 over 2 times x. It won't divide by the x. It'll follow order of operations. It'll say 3 divided by 2 times x. And then, after it calculates the expression inside the parentheses, it'll multiply by that x. So I made that awful big. Should cut down on that just a bit. So I could type it into the calculator. 450 minus 3 divided by 2 times x. Enter the x on the xt theta n button. Close the parentheses. Multiply that by x. And then let's see if we can graph this. What would be appropriate x values that we might input here? Would it make sense for x, the width of the fence, to be less than 0? No, that doesn't make sense at all. If x is 0, it doesn't quite give us a fence. If x is a little bit more than 0, though, although it's not very wide, that technically would give us a fence. So I think we could go as far to the left as 0. So I'm going to set the x min at 0. The x max, we talked about this a little while ago. If we go 400, make it 450 feet wide, and then 450 feet wide, wow, that's way too much. I can't get close to that, can I? Because I don't even have I have the one side, the interior partitioning wall, and I don't even have anything for the other side. I guess what would the extreme be? 300? If we make it 300 feet wide, and then 300 on the other side, and then 300 for the interior partitioning wall, there's nothing left for the top of it and for the bottom of it. That's it. If we go 299, there would be a little bit. It would be sort of like this one over here, just far more narrow than that one. So I'm going to think 300. If we go more than 300, it's going to give us a negative area, and we don't want that. The x scale, what are the increments? If we go 10, 20, 30, there are going to be a whole bunch of them. Could we go maybe 50? Well, I mean, the y value represents the area. We don't want that to be negative. I'm going to set that at negative 100, just so the x-axis isn't at the very bottom of the screen, but we're really not going to consider the portion of that that's below the x-axis. One of the fences we constructed had an area of 30,000 square feet. Another one was around 25,000 square feet. What's the maximum area you think we can get out of this fence if we very cleverly design it to maximize that area? Can we go as high as 40 or 50,000, you think? 100,000? A million square feet? Maybe not quite that much. Let's go 50,000. How close to 50,000 square feet? And I think a Y scale, 10,000 probably appropriate. So if we look at our graph, it'll be 10,000, 20,000, 30,000, 40,000, 50,000 square feet. So graph it. So at 0 and at 300, all the way to the left, all the way to the right, we get 0 area. We don't want the width to be 0, we don't want it to be 300, or we have really no fence enclosure.
My graph doesn't look like that.
Oh, let's see. Well, there are two sources of that. There is the probable. Could be a window here. Oh, it's the right window. Oh, this one. This one right here. When you type in the y equals, you want to type in this. Change that to the, we had 450 minus 3 halves times x in parentheses, and then multiply that by the x. That gives the length times the width. So the ones that we did, second, calculate value. If we evaluate it at 3, no, it was 100, wasn't it? If we make the width 100, the area is 30,000 square feet. Input 100 for the width. The output is 30,000 square feet for the area. if we input 225 for the width of the fence, the output, hopefully that's what we got before, 25,312.5 square feet. What width should we input so the output will be as much area as possible? How much area can we enclose? What if we make the width 110 feet? We can enclose 31,350. Is that as much area as we can enclose? Or could we enclose a little bit more by making the fence a little bit wider? What do you think? You're thinking we can. I know you are. What about 140? We probably can't go more than 33,600 square feet if we make the width 140. But a little bit. If we go second, calculate maximum, and say something between 100 and 200, and maybe let 200 be the guess. I'm going to say the x-coordinate is close enough to 150 to call that 150. If we make it 150 by not quite sure how long it would have to be, we could figure that out. We can enclose 33,750 square feet. Now it is going to ask us though, so 150 feet, and looking back at the calculator, 33,750 square feet is a relative maximum point. And honestly, for the x values that we care about, it is the absolute maximum point. So this is the maximum area. What are the dimensions? 150 feet, 150 feet, 150 feet. That's 450. How much is left? Half of 450? 225? 225 that way, 225 that way. So 150 feet by 225 feet, those are the dimensions which maximize the area. Questions about this one? Can you set that function up? It might be a bit of a challenge. Let's see if we got another challenge in here with the 5 minutes and change that we have left. There's the height of an arrow problem. Going to have to talk about the piecewise defined function next time, but in 5 minutes I think I can talk about the height of the arrow problem. It's an easier problem when the function is given and we don't have to figure it out on our own. In this case, a function h of t is given and it tells us the height of an arrow. And here's the thing, I'm not going to recommend that you fire an arrow from the top of a building. I think that's a really bad idea. Out away from civilization somewhere would be a much safer place to do that. But nonetheless, that's the way the problem reads. So it's fired. The initial height, not a really tall building, but still there are probably people around, and who knows what harm could come to them. So the initial height is 80 feet above the ground. The initial upward velocity of the arrow is 120 feet per second. And this negative 16 has to do with, is not exactly equal to, but has to do with the acceleration due to gravity near the surface of the Earth. But this, well, we don't have to know any of that. The function is given to us if we input a value of t, the number of seconds that have elapsed since the arrow was released. It'll tell us how high the thing is. So I'm going to input that into the calculator, and we'll see how this works. Negative, again, lead with a negative sign, not a minus. Minus gives you a syntax error if you put in front. Negative 16x, got to use an x for this, even though t is given in the problem. The calculator understands the x. To the second power, plus 120 times x, plus 80. I'm going to quickly adjust my window settings. I don't think the arrow is going to stay airborne for 300 seconds. That's a long, long time for that arrow to stay up there. Maybe 10 seconds tops. It'll go up, it'll come down. Hopefully it won't hurt anything or anyone. X scale, 1 second. Along the x-axis, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. I want to know how high that arrow is at any given time. How high is it going to go? It's not going to go below ground level, so I'll set the y min at 0. It's not going to go 50,000 feet into the air. Maybe 500 feet, though. Let's go 500 with a y scale of 100. So with this viewing window, I think it's going to give us a pretty good idea of what this looks like. So here's the graph. This gives the height of the arrow, and I suppose if it's kind of aimed a little sideways, it might mimic the flight of the arrow as well. How high is the arrow at the moment it is released? Second calc value. We just punch in 0. The initial height of the arrow is 80 feet. That's the height of this building, or the height of the building plus the height of the archer. After 1 second, it's on its way up. It goes what? Yeah, 104 feet during the first second, so it's at a height of 184 feet. At the end of the first second, at the end of the second, it's at a height of 256 feet. At the end of the third second, it's just about maxed out, ready to slow down to 0 and turn around and work its way back down. 296 feet. What's the maximum height attained by the arrow? Second calc maximum. Left bound of 2 seconds. Right bound, what do you think? 4 seconds? Ooh, barely. Should I have gone with 5 there? Or am I beyond the top point? You think I'm beyond the top point? I should have gone with 5. Kind of feel bad about that. Enter. I think 3.75 seconds is how long it takes the arrow to reach its maximum height. 0.75 seconds. What is the maximum height of the arrow? Is that the next question? Can we do that in less than a minute? What is the maximum height of the arrow? Can you see the small print? 305 feet. 305 feet. At some point, I will post those test grades. So be on the lookout for that. Otherwise, have a great Friday and weekend.